In section 5.8, we're going to be talking about real gases. All the gases we've talked about up until now were gases that behave ideally. In actuality, no gas behaves exactly as an ideal gas. This is in a perfect world. So we need to talk about real gases. When we look at revisiting the Maxwell distribution for molecular speeds, this is just a rough sketch. Of course, the black line represents the molecular speeds at a lower temperature, and the red line is a little more flattened out. The molecular speeds at a higher temperature will have a higher average speed. But at any given temperature, all gases have the same average kinetic energy. And the gases with lower molecular masses will have faster average speed. Like we talked about before, things that are lighter travel faster. Real gases do not follow Pivnert perfectly. The van der Waals equation listed below corrects for the non-ideal nature of real gases. We have a correction of n squared A over V squared to correct for pressure, and we have to take n times B and subtract that from V to correct for volume, and we'll talk about these later. The A stands for the correction that needs to be made because of the interaction between atoms. When we said that there were, according to the KMT, there were no attractive forces, no repulsions or no attractions between gases. In real life, gases, when those molecules get close enough to one another, they can experience attractive and repulsive forces. So there is some interaction going on between these. B then corrects for the volume occupied by atoms. We said in the KMT that the volume of the gas compared to the space it takes up is negligible, and we say it's 0. When in all reality, we know that these gases, the particles really do have a volume. So for real gases, we use the van der Waals equation that corrects for both of these cases. So the van der Waals equation is just one of the several modifications to the ideal gas law that tries to describe the behavior of the real gases. So the V ideal becomes V observed minus n times B, and B is that constant we talked about in the previous slide. P ideal becomes P observed plus A times n squared over V squared. And so we can plug this in to get P plus A times n squared over V squared times V minus NB. It looks very similar to the one on the previous page. Equals nRT. Now, if you need this, this will be on the formula sheet for the AP exam. I'll double check the 2014 formula sheet because there were some changes, but we'll make note whether it's there or not. I'm pretty sure it's going to be because they haven't tried to make things more difficult. They just tried to do more depth about what we're teaching. So as we stated, A and B are both van der Waals constants. They can be found in reference tables, and if they're not, then they're given in the problem. They're not things you have to memorize. One of the things that is mentioned in the book, but I don't really see it here on the PowerPoint, I just want to make note of it, that the real gases do behave more ideally at lower pressures and higher temperatures. And the reason is the less pressure there is on a gas, the less you're pushing those molecules close together and the less attractive and repulsive forces they will have. The higher the temperature, the faster they'll go. And the faster they're going to move, again, the less forces they're going to feel on one another. So do make sure you make note of that in your reading. Here are two example problems. The first one is just asking you which one would deviate more from the ideal gas behavior. So you're going to take a look at probably their molecular mass and maybe some other things. You can also, if you need the van der Waals constants, you can look at the chart in the book. But for example, too, the van der Waals constants are given to you. I think at the bottom, A is supposed to be 5.570 liters squared times ATMs over moles squared. And then B is 0.06499 liters per mole. Again, sometimes the translation of these from one to the other, we lose some of those symbols. Give these a try, make note of any questions that you have, and when you come in tomorrow, we'll be doing some problems with real gases.